Well, we're going to move right into the part of my video here that will talk about the actual study itself. And we'll see how we can get through this. First I want to start off with is I just want to thank the Usgs not only for their hard work on the study, because I've really enjoyed working with Megan, very positive, always very prompt and great to work with. And Mike Feenan, I mean, I've talked to him a couple times, but he's been really great too. But even though I don't agree with the results of the study, I think it's really important. Of course, anytime you have a hypothesis and you hope for the right results, but I think with you guys being unable to be on site and to check things out, I think it makes it pretty hard. And for me in my daily work, you know, I'm wrong quite a bit too. And I'll say when I get the wrong result, I got to kind of make a new hypothesis, and the physical results have to match. And if they don't, you got to kind of start over. So, but at any rate, this document right here I found on the USGS website back early on in my project. I've got a few copies of this. This one I haven't all scribbled up or anything like that. But it discusses everything a person wants to know regarding hydrology. And I really appreciate that being available, so thank you for that. I've learned a lot from that. Going in from there, of course, you're familiar with this, the 1990 water study. You guys referenced that in your study. Then the scope and purpose, this is the proposal. Basically, I guess we're only trying to answer a two-part question, determining whether or not the Crex Meadows water levels contribute to groundwater flooding at adjacent properties, and if they do, how far does it go? And the conclusion that the USGS reached in this study right here is that no, it doesn't affect anything outside the Crex Meadows, and so the answer to number one, as far as they're concerned, is no, and as far as number two, doesn't really apply. So I hope you enjoyed the field trip. I don't, you know, like I said, I mean, this picture here, I mean, look at how tall the grass is and stuff. I mean, it's well into the growing season here. That first part of the video should have been enough right there, but I'll move right into some of this stuff. Okay, the first thing that concerns me about the study, just how you put it together, is you guys have hypothesized based on a well here, that WB41, as it's written up here. And okay, so the first thing is that well is located 42 miles away. It's not in the same aquifer, same local aquifer. There's lots of rivers and roads and stuff in between. You've both pointed out to me before that roads change gradients and all these different things. And I think you're trying to identify in the study there that you're making a comparison on water trends and things like that. And yeah, that makes sense. But again, that, in my mind, that's just a theory. It's not really a proven thing. Something here, this is referencing well 11 in the study area, and it really doesn't matter which well it is in my mind. But when you look at this, I can see the trends you're talking about. The well that's 42 miles away kind of goes down and up. This one locally goes down and it goes up. But here's something that's kind of odd. When you're going to represent two graphs together, this one starts out at 970.6, and in 1/10 of a foot increment goes its way up to 971.2. So each one of these lines here is just 1/10 of a foot. But when we go down to this one, it starts out, you can see they're in 1/2 a foot increments. To me, if you're going to do a visual display side by side, you want to make sure they're to the same scale. If you do that, which I have done, this is a much flatter line. And yeah, so I just think that's kind of something that's important. If you're going to have visual displays next to each other, you got to put them on the same scale. Something else regarding this well in particular is I don't know where this scale came from. I've got it up on the computer here, and this is off the USGS website. It's available to anybody to see. And you can see that's the well number that's referenced in the study, and there's the WB41. But the elevations here start out at, let me move my mouse here. 1079.6, and they go all the way up to 1080.3. And again, they're in tenth of foot increments. Now, if that's this well, why don't them elevations match up? I expected, Megan, you'll probably get back to me on that because you're always prompt and polite and, like I say, positive, and I really appreciate that about you. So that's one thing. I don't like the fact that you're hypothesizing. I don't like that these numbers don't match what's on the website, and I think they should be to scale with one another. So that's one thing. The next thing is, I'm going to put this together here. Sorry I'm moving around so much. I don't want to make anybody sick with all my movements. But in the study here that you put together, and by the way, I want to point out, I mean, you do at least mention that there was 7.7 inches more rain in 2019 than what's normal, even though we had dry ditches here. Okay, where are we at here? Get groundwater elevations. I'm trying to get to the gradients page. Sorry I'm taking so long. And by the way, I do understand this report. I've been going through this stuff enough over the last 3 years that I understand them fairly well, I think. All right, so right here we're looking at horizontal gradient between well 1 and well 10. Well, well 1, that's Dike 6 flowage, and well 10, that's the USGS long-term well area. It's not the data from the new long-term well, I understand, but you know, same spot. That one is very valid. I like that one, and you can see the gradient there. You guys got it in feet by feet, which, you know, when we've talked gradients in the past, we've always talked about feet per mile, but I would guess, you know, you just multiply that number by 5280 and I get my number. No complaints there. But what I don't get is each one of these is in relationship to well 10. And, you know, there's no human intervention, let's say, between well 10 and well 4 or well 3 or well 8. So, I mean, we're not going to see any changes, in gradients between those particular wells with human intervention at, say, well 1 at Dike 6. I kind of, from what I'm finding, the gradient stays pretty much the same between all the other wells when there's changes made at Dike 1 and also at Dike 9. And I think that's a really important thing to point to make. I think you guys would agree that if you had a couple wells that were, let's say they're a mile apart to make it easy, and the elevation was, say, 950 at the high end, and you go a mile away, the low end of that is 940, we'd say that's 10 feet per mile, right? Well, if I raise it 4 feet on each end, you still got the same difference. It's still 10 feet per mile. So that's why I feel, you can't really compare from well to well. You have to compare it to a baseline being like Dike 6 or Dike 9. And to be honest, I think I've mentioned this before. I don't think Dike 9 has it doesn't make a huge problem for anybody but Roxy and I. I think the elevation of the water there would be pretty tough to affect other properties than ours, given how it's, the proximity of other houses and that kind of stuff. But at any rate, I went ahead and I ran you guys' numbers. This took me a fair amount of time. And I find that, I agree with your numbers. I just don't agree with how you did it. One thing I will point out that's kind of groovy, I guess is a word I'll use. During my field trip video, I ended at Dike 9 flowage, which is well 7. And the well right at our house, our property in Bester Road, is well 8. So I did a 3-day rolling average also. These are 3 separate dates here, where we started out the study in 2019. This is where it was lowered and stabilized as much as it could. And I do want to remind you that I did point out that I didn't think it was right to put the boards back in again so soon. And the whole reason for that was the groundwater was still dropping very quickly on our property and at the other wells or my other test locations as well. I think it would have been really, really important to leave the boards out even longer, because then you'd see a net difference of much more water, and it leaves less question to whether or not there's really an issue. So anyway, started the study, lowered, raised using the USGS well numbers. And like I said, the wells are very close together. It's 0.06 miles if you convert the feet over. And it's kind of crazy here. I have an upward gradient of 27.33, then a downward gradient of 2.67, an upward gradient of 17.3. And that kind of goes right back to what I talked about that at the end of the field trip, how they have a kind of a crazy triangular relationship. And these numbers show it in my mind. And that's in addition to what I witnessed with my own eyes. So now I'm going to move over to here. All right. There were 2 studies done. I mean, you're well aware of that. Here's 2019. And of course, that is well number 1, Dike 6 flowage. This is where the boards were. This is the beginning of the study, even though the water was even higher than that prior to the study, but they lowered them just for you guys. So boards were taken out, and like I said, I wish they would have been left out longer because this number would have kept dropping. And right here, boards back in again. And this right here, by the way, this that if I look at that on the date to that, that's right when we had our conference call, by the way. But nonetheless, water came up again right there. And then in 2020, this is again, Dike 6. You can see here's where the boards came out. And I'll mention also, right in the beginning here, if I go look at this closer, I think I emailed and mentioned that the DNR had put a board or 2 in there. I went to Florida to watch softball, and I don't think they told you that they did that. But nonetheless, I'm right here. I check things very closely. I think I'm acknowledged in the front of the USGS study for that, and I'll tell you, I don't really want my name in that study. I think the study should be retracted, to be honest with you. Okay, so now this one. This is the long-term well that's been put in place back in, looks like December of 19. And so basically this is the date that matches up with this green line. So this is a segment of time here that matches. This is 2.36 miles away from this well. So, I mean, when you take the boards out and it drops, and then this is 2.36 miles away, that also drops. That's 3.3 feet, according to the website here. Now, I know you guys are going to talk about trends a little bit. So when I go back to this WB41, you can pretty easily look through here, and you can kind of see that, it's only really half a foot that it changed. And, half a foot, my goodness, we could take a half a foot off of 3.3 feet. And geez, we still got all kinds of water that dropped there. And actually it's probably more equitable. So I think that's a really good point that you brought that up. I mean, with precipitation or whatever it was. And I think that trend in WB41 is actually believable. If we subtract that 6 inches, 5 or 6 inches of what it was from here, that's probably about the amount of water that was removed out of Dike 6 flowage. And this is kind of the same thing here that I was talking about before. Each of these squares are half a foot increments. This one is in 1 foot increments. So it's a little misleading when you look at the graph itself, but nonetheless, I wanted to point those things out, and I would like a response on those. The physical results, as you see in the field trip, are mind-boggling, to be honest with you. I didn't actually think the water would go down quite as far as it has. I don't think the water's ever been that low since we lived here, and all that. So this document here, this is something I put together, obviously after the 2020 study stuff is done. And what I have here is I've got all the wells listed that were actually in operation in 2020, because some of them were removed from the 2019 study. And I've got them listed here. And diagonally I've calculated the gradient. So I've got the change in water elevation, and I've got, calculated the gradient. And regardless of what I'm finding is, regardless of what elevation that Dike 6 is at, the gradient stays pretty static between the wells that are located west and south of the flowage 6. All right, here's a document that I made. This is using 1990 or the 19 study results. Here you go. This is on the edge of the flowage. That's your actual graphs off your site. And then when you go down to the one by Jerry Fiedler's, Bistrom Road, there's results from that. And you know, the thing is, these are all kind of on the same date range, obviously. And here we have, this is the well on Guile Bistrom Road. This would have been the original well that was there. And that's like I said, 2.3 miles away. And see how it's kind of lower on that end? Came down and came back up. Well, if you remember, you know, we started the study much lower than where we ended because I complained so much about not starting the study at 937.8. So they raised it, we were able to get it up even higher. And I would tell you that if it didn't take us so long and there's actually water in reserve to fill this back up again, it would have went up even quicker because it took forever to get the water moved in there. If we were going to conduct a study that was fair and honest to everybody involved, we would have that water on hand instead of having to pump it all over the place from North Fork and so on. And I'll have some videos ahead here talking a little bit more, but this is just about the study here. So, but at any rate, so these show that. The Village of Webster well, you'd mentioned to me that I probably shouldn't use that because it's a high capacity well and what have you. And, you know, that doesn't fluctuate that much. I mean, when you look at this and, you know, we go by the dates that I put together and you look at the starting date and the ending date, wow, it's almost like there's no change. I mean, it's pretty solid, you know. So I guess for me, I mean, if you're going to have a well on the website, people should be able to use it for these purposes. But otherwise, I don't mean to beat up on you and Mike because I really appreciate you guys a lot. But otherwise, so them are my major questions with the study. I see you got a really nice deal here for help people understand how to calculate a gradient, I guess, whether it be up or down, however you want to look at it. And yeah, so that's that deal. The last thing I have on the study itself, I'll share with you, is this right here. I took the time, these are done based on a 3-day average. You got one for the 2nd of July, and this one's for the end of October, and this one here is for the 1st of September. And you can see where I've got my gradients here. I used Usgs well information, which you'll see here, and you can see the gradient to water actually goes this way right here. But this on Pete Nelson Road during my field trip, if you remember, there's a drainage ditch that goes right through here. And I'm sure that has something to do with it. But nonetheless, I worked pretty hard on these things. And not that my hard work means that I'm right or anything like that. But one thing is I want to point out on my gradient maps here, that the Crex Meadows had absolutely no effect on our property. When I draw my gradients based on your well elevations, and I mentioned in the video, by the way, that I felt you were off by 0.8 feet at dike 6 flowage. Even the well information kind of shows it. The duck pond right down here next to County Road F is at 935.16 for a 3-day average for the period that I picked. But the groundwater at dike 6 is only at 934.17. And maybe you've got a reason for that, but I would say, you know, there's a big drop of water here, you know, down through that culvert, and there's another big drop right here. But these kind of gradients, to me, if there's no effect, they stay pretty rounded. It isn't like there's a wall of clay all the way from the next aquifer layer, the clay layer underneath, all the way up to the top. I mean, for this to happen, it almost has to have a natural drop off. And you know, the elevation of the soil or the bottom of dike 9 flowage area, you know, it jumps into this ditch here, and then, you know, it changes gradient huge. So this is why I see the water flow right out of our property and go right into there. It can't be natural with them hard curvatures like that. And even this one shows it. And, you know, I didn't just pick the numbers out of the air. I went through that pretty closely. But anyways, so there's a little bit with that. So that's all I have on the study itself.